Hello, 6.1 notes, exponential functions and logarithms. Here we go. Get excited. Go ahead and copy this down real quick. Okay, so we have our exponential function. F of x equals a times b to the power of x. So, I have right here, if b is greater than 1, this is an exponential growth function. And right here it says if b is between 0 and 1, which means that b is some decimal number that's less than 1, such as, 0.5. If b is between 0 and 1, it's an exponential decay function. Now, a is just a number, and so is b, but b is what we call your base number, and then x is your exponent. So this is not b times x, this is b to the power of x. That's why they call it an exponential function, because your variable x is in the exponent. So let's keep these rules in mind, because on the next paper, we're going to see how to answer if something's a growth or decay function. So go ahead and copy these down real quick. Okay, so we're going to tell whether the following functions are exponential growth, exponential decay, or neither of them. So let's look at part A. We have f of x equals 3/4 to the power of x. Just keep in mind that an exponential function, like we just saw in the last paper, is a times b to the x. Well, we do have an x in the exponent, so this has to be growth or decay. It all depends on what your b is. So let's see if we can identify what is a and what is b. In this problem, a is just a number that comes at the front. Now there is no number here. Well, we don't see a number written, but we assume there's a 1 there, so our a value is 1. We don't really care about the a value, but I just want to point out that a is equal to 1 in this problem. However, b is whatever is being raised to the power of x, in this case, 3/4. Now, 3/4, we have to ask ourselves, is 3/4, is that greater than 1, or is it between 0 and 1? Well, 3/4 is the same thing as 0.75, and that is between 0 and 1, which means that this is a decay function. Look at part B. X is in the exponent. Our a value is 2. We don't really care about that one, though. We just want to know our b value is 1.07. And that is greater than 1. So this is a exponential growth function. Part C, we have g of x equals x squared plus 4. Well, look at where your variable is. This is not to the power of x. It's just x squared. This is actually a quadratic. Remember quadratics from a while ago? And we see them all the time. Don't they always pop up? Can't get rid of them. So this is actually a quadratic, which means it's not an exponential. It's not an exponential. Which means it's just neither. That's all it means. So that's our answer, is neither. It's just a different function. It's one we learned a while ago. That's all it means. Alright, so we've seen decay, we've seen growth, and neither. So it's just about identifying your b value, and then is it between 0 and 1 or greater than 1? Or is it even exponential? Okay. Here's the growth and decay formula for word problems. So we have a of t equals a times, and if you want, you can put a little dot there. You don't have to, but that is read as a times all of this. And what is this? This is 1 plus or minus r, and then this parentheses is raised to the power of t. Now, a of t is your final amount of whatever you're looking at. It could be money, it could be It could be bacteria, like, measuring the growth rate of bacteria, carbon half-life. There's a lot of applications with this formula. Little a is your initial amount. It's how much you start off with in the problem. So whatever you're starting off should go right here on the outside of the parentheses right there. 1 is just your number 1. We'll get back to the plus minus in a second. Sorry, let me get my hand out of the way. But R is your rate of increase. Now I say rate of increase, but it might also be your rate of decrease. But R is your rate of increase, and actually I want you to make a note. Sorry, I didn't write this earlier, but for the rate of increase, or for R, you need to convert from percent to decimal. If it's not given as a decimal already. If it's not given as a decimal, you need to convert from a percentage to a decimal. And I'll show you how, because we will do a word problem together on this. T is your number of time periods. So if the problem tells you find how much bacteria is in a sample after 5 weeks, T would equal 5. So T is just number of time periods. It could be weeks, it could be hours, it could be minutes, it could be years. Just depends on the problem. Now, the plus or minus, so when you're doing a word problem, you're not going to use both the plus and minus in the same problem. You're going to use the plus or the minus. You're going to use the plus if the amount that you're starting off with, your initial amount, if it's going up, if it's increasing. That's when you'll use the plus. However, if your initial amount is going to be going down, getting smaller, then you want to use the minus instead. So do not use plus and minus in a word problem. Use one or the other. It all depends on the problem, though. So here, I'll show you right now. I'm going to copy this word problem down. Try to keep it pretty short to copy. Let's take a moment, pause. Okay, so we have the value of a truck bought new decreases 9.5% each year. Write an exponential function with this information, then estimate how much the value of the truck will be after 17 years. So let's highlight some key information here. Decreases 9.5% is very important here. I think we're missing information here. So let's say the truck is bought. Yeah. Oh, I forgot to write this down. Sorry. Let's say we buy the truck for, I don't know, $28,000. Okay. So we buy it brand new at $28,000. Decreases 9.5% each year. We want to find how much it's going to be after 17 years. So we're going to write the function first. Then we'll plug 17 in and see how much this truck will be worth after 17 years. So, remember the formula is A of t equals A times 1 plus or minus r to the power of t. So let's just get some information down real quick. What is A equal to? What is our initial amount? Well, we bought the truck initially for $28,000. I'm not gonna use the dollar sign anymore, or the comma. So A is equal to $28,000. Because this decreases, are we gonna use the plus or minus? We're gonna use the minus sign. So we're gonna use the minus sign here. R is 9.5%. But like I said earlier, we need to convert the percentage to a decimal. Now here's how you do it. Here's the fast and easy way. You have 9.5, right? You just take the decimal, and you might know this trick already. You just take the decimal and move it 2 places over, like this. Put a new decimal here. Now, see how we have a little space right here? We need to put a 0 there. So our actual rate, we're not going to use the percentage anymore. We're going to say that R equals 0.095. Okay. Another way you can do this as well, if you don't like moving the decimal by hand, you could take the 9.5, the 9.5, and divide it by 100. If you have your calculator, I don't have my graphing with me. If you take 9.5 and divide it by 100, you get 0.095. But that's what I just showed you right here as well. Okay, and then t equals 17. So let's go ahead and write the function real quick. We're just plugging numbers in. A becomes 28,000. Parentheses 1. Now we're choosing, like you said, we're going to choose the minus sign. And we're going to plug in r as 0.095. And we're going to keep the power t for the moment, because the first part of the problem did say write an exponential function with this information. And then we'll find out when t equals 17. Now, here we are, but can't we, on the inside, can't we do 1 minus 0.095? Yeah, let's go ahead and just see what that is real quick. So I have 1 minus 0.095. And so my decimal is 0.905. So let's just rewrite our function slightly. So 0.905 raised to the power of t. Alright. See, the great thing about having this function is, what if I wanted to calculate the value it would be after different amounts of years? What if I said, give me the amount for 5 years, 10 years, 15 years, 20 years, so on? Well, you have this function. You can just plug in whatever values of t that you want to plug in. That's all you have to do. So, but in this case, in this problem, and I'm going to switch colors here, we're just plugging in 17. So that means that we're finding a of 17. Remember, that's how function notation works. We replace t with 17 here, but we also replace t on this side. So I have, instead of power t now, I have power 17. On my calculator and on your graphing calculators, we can just plug this all in one shot. You should be able to just do 28,000. I'm hoping this shows up pretty well on here. It looks like it is on my phone, but 0.905 raised to the power of 17. Remember, on the graphing calculators, how do you raise to the power? You hit the caret button. Anyways, that's all we have to plug in. And so after 17 years, this truck that we bought for $28,000 after 17 years is $5,130, and because it's money, we're around this is 79 cents. That's insane. You buy a truck for that much, and after 17 years, it's down to that. That's why people usually say don't buy cars brand new. By the way, little life lesson, right? So we answered the question. There it is. All right, a few more things I got to show you. Is introducing logs. Actually, I want to kind of cover up this part real quick. Logarithms, that's how you say it, and yes, that's the word, logarithms, might seem like a very weird thing at first. Might seem like, why are we doing logarithms? I'm going to try and break down why. You should know how to answer this question, at least. If I ask you, solve for x, well, it's just a one-shot thing, right? 2 to the power 3 equals x. Well, just calculate 2 to the power 3. That's 2 times 2 times 2, which is 8. So we know that in this problem, x equals 8. That's easy. But that's because we knew our base, 2, and we knew our exponent, 3. And x was just down here. X is just right there. But what happens when I give you the same problem, but I rearranged everything slightly where I give you 8, I give you 2, but I don't give you the power. How do you solve for the power of x? Well, logarithms help you do that. Now, you might be thinking, well, I know that x is equal to 3. Even if I didn't know this at the moment, I could look at that chart, we learned in the last chapter and say, oh, I'm just asking myself how many times do you have to multiply 2 by itself to get 8? 3, obviously. But what if it wasn't so easy like that? What if I gave you something like 4 to the power of x equals 23? And actually, 4, 4 times 4 is 16, times another 4 is 64. So there's no whole number, x value, that you can raise 4 to the power of to give you 23. However, a decimal exponent would give you 23 somehow eventually. So logarithms help us tackle this kind of problem. That's the whole goal of logarithms. Now, I'm going to show you what a logarithm actually is. You haven't seen it yet. So here we go. You have an exponential equation. We have b to the power of x equals a. We can take this equation and rewrite it like this. So what I'm saying is these two equations are the same exact thing, but they've just been rewritten in different ways. This is the exponential version of the equation because x is in the exponent. And what happens is you rewrite this as log, and we call it log base b of a equals x. So what happened from here to here? A few things happened. The b that was the base of the exponent x is the base of the logarithm. So they're both bases in this case. Here's a big base, and here's the base of the logarithm. Then we have the a right here. So the a that was on the right side initially is now on the left side. And then it equals whatever the power is, which is x. So one way I think about this, by the way, and this may help you guys know how to like flip back and forth between these versions, is I always think you can raise the base b to the power of the other side. When you move the b to the other side and the b pushes the x up as its exponent, the log goes away and you're equal to a. And so that's how you can get back to this form. Okay? That I know that might be a little confusing at first. It takes time to get used to, and that's why you'll practice in class, but it just takes a little time to get used to that. So I threw an example on here. I said 3 squared equals 9. Obviously, we know that. But how do we rewrite this in log form? Well, the 3 that's the base here is the base of the log. And then what are we taking the log of 9, which is the other side, and then it equals whatever the power is, which in this case is 2. Okay, so these are the same exact equation, just written in different ways. The reason why we use logs also is, see how here we have an exponent? A logarithm is just a way of writing an exponential equation so that we no longer have an exponent. We no longer have an exponent, which is useful in some cases in math. So I'm just going to do a few examples with you guys, and we'll stop there. So we're going to rewrite each exponential equation into log form. So if you look at each one of these, they all have an exponent. Here's an exponent of 6, here's an exponent of 1, and here's an exponent of 0. We're just going to rewrite this into log form. So each of these should have a log. So I'm just going to go ahead and do that now. They all have a log. Okay, so what is the base? Let's do part A first. What's the base of this log? Well, what's the base of the exponent? 6. The base of it is 2, so I have a little 2 here. Then what's the big number that goes right here? So I have log base 2 of what? Is it 6 or 64? Well, it's whatever's on the right side, so of 64. And then it equals our exponent, which is 6. That's how you rewrite. Once you get used to it, it's pretty easy. It takes practice. All right, let's do this one. What's the base of our exponent here? Well, we have a base of 4. And then we're equal to 4, so we have log base 4 of 4 equals 1. Let's do this one. Try this out yourself, actually. Take a moment, pause. See if you can do it. All right, so hopefully you paused it. Maybe you tried it out. What was your base? It was 5. Then you had a 1. And then it equals your exponent of 0. All right. Seems like pretty simple stuff. So we're starting off pretty easy with logs. Then the last thing I want to show you is just going the other way around. how do we rewrite from log form to exponential form? We're just going backwards from what we just did. I'm going to switch colors here. So the base of this logarithm is 10. So that means that I should have a 10 to some power. Let me just try and explain again how I think about this. Raise 10 to the power of the other side. So 10 to the power of 2. Then equals 100. And you know that's true. 10 squared is 100. So this is a true statement. Remember, these are the same thing. All right, let's try this one out. So my base of my logarithm is 8. That means I should have a big 8 here. To the power of what? -1. Equals the big number right here, which is 0.125. Oops, sorry. And again, you can verify that if you want. 8 to the power of -1 is 0.125. Well, there you go. Don't forget to like and subscribe. And I forgot my math joke. I'm so sorry. Have a great day, guys.